We've been discussing energy. There's a quantity related to energy, and that is power. Power is how much energy is used or produced in a certain amount of time. So power, you take the work done, divide by time, take the energy released, divide by time. That would be the power rating, the average power. The space shuttle, with 3 main engines and 2 solid rocket boosters, was rated about 12 billion watts. A watt is 1 joule in 1 second, energy use of 1 joule in 1 second. So the space shuttle, 12 billion watts. 12 billion watts. A typical home would be about 2,000 watts, would be its power rating, power usage. So 12 billion watts for the space shuttle, 2,000 watts for a typical home. So let's take a look at some physics of power calculations. If we have a person walking up the stairs, do they produce work? Is work being done? You should say yes, because potential energy is higher than it was at the start. There's been work done against the force of gravity, and that work would be mgh. Suppose the person goes up the steps in 10 seconds, and then the person repeats the experience but goes up in 5 seconds. Is the energy different in those two cases? Person goes up the same set of steps, once in 10 seconds, another time in 5 seconds. Is the energy different? Is the work different? No, it's still mgh. Both situations, mgh. But the power would be different. You could calculate the number of joules with mgh, divide by 10 seconds in one situation. That would be the power rating. Or take that same number of joules, divide by 5 seconds. If the work is being done at a faster rate, that would be a higher power rating. So our power measures how much work is done in a certain amount of time. If some mechanical system has greater power, it can do more work in a given time compared to a machine that has less power. So more power, you can get more work done in a given time interval. So that's related to energy. A little quick calculation on power. If we would have a person then running and changing chemical energy and food and stored in the cells of the body, again, that would be an energy output and divide by a certain amount of time. You could calculate that power rating. We're not going to do so. But that was sort of situation for power. How much work is done in a certain amount of time? Just to emphasize this definition, let's do a few calculations. Again, average power is the work divided by time. Suppose we do 100 joules of work in 1 second. There's 100 watts, a light bulb. 100 joules in 1 second. 100 joules, but if we require 2 seconds to do that work, it's 50 watts would be our power rating. And 100 joules in 10 seconds, 10 watts would be the power rating. As the length of time goes up to do a certain amount of work, the power rating is a smaller number. Again, watts are the metric unit of power, and you're used to those from appliances or especially light bulbs. So let's talk about the generation of power just a little bit. It's a important part of civilization, having electrical power and other forms of power, but electricity being illustrated here in this diagram. Burning fossil fuels, coal in this situation, and we'll study more about the production of work from situations like this where there's some source of high energy, heat, high temperature, and energy going into the environment, waste heat. We'll study that more in a future chapter. Where is energy being generated in 2006? So this shows petroleum, coal, natural gas. Petroleum, coal, natural gas, fossil fuels. They have an unfortunate byproduct of pollution and carbon dioxide released into the atmosphere. They are cheap. The economy is driving the use of the fossil fuels. We want energy to maintain a certain lifestyle, to maintain a certain economy. And the fossil fuels are currently providing that. Speculation on the increase in world energy consumption, and 10 to the 18th joules being the scaling on this particular chart. There are going to be more people in the world. People are going to want higher standard of living. Economies grow, and that results in more energy being consumed. Some alternatives to the fossil fuels would be renewable sources such as solar and wind and hydropower. This is a slide from Germany that has undergone a program of trying to use solar energy in great amounts. So along the interstate highways, along railroads in Germany, you'll find banks of solar panels converting solar energy into electricity. We are concerned about the use of fossil fuels because of the measured increase in carbon dioxide in the atmosphere of the Earth. So this is going back before 1960 up through the early years of the 2000s. And we can see a steady increase, and maybe not steady is not the right word, it's an increasing use of carbon dioxide, a growing use of carbon dioxide, and being placed into our atmosphere. Not use of carbon dioxide, but placement of carbon dioxide into our atmosphere. And burning the fossil fuels is a great contributor to this. Also, cutting down forests, not having as much plant life on lands contributes to more carbon dioxide in our atmosphere. Our atmosphere is relatively thin. The bulk of our atmosphere is within 10 miles of the surface of the Earth. The atmosphere goes up, there's no top to the atmosphere, but you can see meteors produced around 50 miles above the surface of the Earth. So there's air up there, but it's very thin. The bulk of our atmosphere, I've read in some source, is about 10 miles, within 10 miles of the surface of the Earth. And we want to take care of that. It's very important for us for breathing. It's also important regarding greenhouse effect and the temperature on the surface of the Earth. Planet Venus has a runaway greenhouse effect where its surface temperature is around 800 degrees Fahrenheit. It has a very thick carbon dioxide atmosphere. And the greenhouse effect is a situation where the sunlight filters down to the surface. The planet receives that light. It tries to radiate the same energy it receives as infrared, and the greenhouse gases block that. And perhaps blocking is too strong a term. The greenhouse gases limit the amount of infrared light that gets out into space. In order for the planet to send to space as much energy as it receives, the planet's temperature has to increase. The greenhouse gases, carbon dioxide and methane, are absorbing a certain fraction of the infrared light that passes through the atmosphere. So to get enough energy through the atmosphere, more energy has to be emitted at the surface because more is being trapped by the greenhouse gases in the atmosphere. So planet temperature rises, and that's not without some bad effects, maybe some positive effects. For if you live in Canada and you like warmer winters, then maybe some places on Earth will have positive effects. Now, there is correlation between carbon dioxide concentration in the atmosphere and temperature rise that's been occurring here. It's more complicated than we can go into, but there is reason for concern, reason that this should be studied in great detail. And the greenhouse gases, carbon dioxide and methane, need to be better understood. There are computer models that show dire consequences of sea levels rising and climate change occurring. It needs to be studied more, and citizens of the future will have to take some action, make some decisions. Correlation between greenhouse gases, carbon dioxide, and temperature in the past. Drilling ice cores reveal this. There has been natural change of carbon dioxide in the past. And energy use, the United States has a great energy use per person. So I'll just leave you those things to consider.